Let's take a look at the acronym phrase ELI the ICEman. Let's see how we can use this without getting into too many technical explanations like imaginary numbers or a whole bunch of calculations. So what does this mean? Well, a long time ago, E represented voltage because it was also called electromotive force. So ELI means that voltage for an inductive circuit leads current. And the ICEman part reminds you that for a capacitive circuit, the current leads the voltage. So if we take a look at this little vector diagram here, voltage for an inductive circuit would lead the reference current or reference voltage. In a capacitive circuit, the current would lead the voltage. That's the ICE, I, capacitor, and the voltage of the capacitor is behind the reference current. So if you were to use the impedance formula here, Z equals square root of R squared plus parentheses XL minus XC squared. Let's remove the inductor, so we have no inductance, we're only using a capacitor, and we pretty much get the Pythagorean theorem, Z equals square root of R squared plus XC squared. And for our practical example, I'm going to use 6.8 kilo ohms for the resistor and 0.01 microfarads for the capacitor, and we're running at 4 kilohertz. So if you plug in these numbers for the reactance and calculate an impedance, or let's just calculate reactance, you get XC equals 3978 ohms. And if I take the inverse tangent of that with the resistor, I'm going to get this angle here of 30 degrees. So how do we verify this with a practical example? So what I'm going to do is I'm going to measure some voltages. Here is the circuit. I've got a resistor and a capacitor in series, and I'm measuring across the capacitor right now. You can see here on the oscilloscope, channel 2 is the green. I have it lined up with the divisions, the major divisions there, and it's at 0.5 volts per major division, and I have about 3 major divisions peak to peak in channel 2, so that gives me 1.5 volts. I've represented that here in this vector diagram as 1.5 volts going down for VC. Now let's take a measurement across the resistor. So I've switched the order of the components, but they're still in series, and this is simply to make it easier to take a measurement across the resistor. Here on the oscilloscope, you can see the green line represents the voltage across the resistor on channel 2, and channel 1 in yellow is the resultant vector or the circuit. So if I line this up so that I can count the divisions, you can see that my peak-to-peak voltage for the resistor is 2.5 volts. 5 major divisions times 0.5 volts per division, 2.5 volts. So I'm going to line this back up again with their centers. And let me show you here on the vector diagram, I've represented that for VR as 2.5 volts going towards the right here. You can calculate a resultant vector here using the Pythagorean theorem. But right now I'm interested in finding out this angle here. So how can we do that on the oscilloscope? Well, if you take a close look here, notice the green line leads the yellow line. So the voltage across the resistor leads the resultant vector, and it's a little more than 2 small divisions. I'm going to call it 2.1 divisions. And if you look at the bottom peaks there of the resultant vector, 360 degrees would be 5 major divisions. And 5 major divisions is 25 small divisions. So again, the difference between the signals right here is about 2.1 divisions, and 360 degrees is from this peak to this peak, which is 25 divisions. If we do the math, 2.1 divisions divided by 25 divisions times 360 degrees gives us 30 degrees. Lo and behold, the 30 degrees between the voltage vectors matches what we did earlier with the vectors for the reactances. So remember ELI the ICEman. In an inductive circuit, the voltage leads the current. In a capacitive circuit, the current leads the voltage.